Hello everyone, I am Savindra, a freshman from the Civil Engineering Department at Paragon University. In this video, I will be explaining about trigonometric integrals, which is a subchapter from chapter 8, Techniques of Integration. And here's the learning objective. After you finish watching this video, you will be able to use trigonometric identities to evaluate integrals of trigonometric function. And here's the table of contents. So first we start with definition of trigonometric integral. So what is trigonometric integrals? Trigonometric integrals involve algebraic combination of 6 basic trigonometric functions. In order to solve this type of integral efficiently, we must use trigonometric identities. Below are some of the most used trigonometric identities to integrate trigonometric integrals. We will use most of this in our next slide, so let's move on. Next, products of powers of sines and cosines. So when an integral is in this form, which is integral of sine to the power of mx, cosine to the power of nx dx, where m and n are non-negative integers. When we face this situation, we must follow these procedures, which is divided into 3 cases. Case 1 is when m is odd, and case 2 is when m is even and n is odd, and case 3 is when both of m and n are even. Now, if you find this explanation a bit complicated and long, there's a short and simplified version that I found, which is case 1. If power of sine is odd, keep one factors of sine, and then use Pythagorean identity of trigonometric function to change sine squared x to 1 minus cosine squared x. Case 2 is the same, except when the power of cosine is odd, you keep one factor of cosine and then use Pythagorean identity of trigonometric function to change cosine squared into 1 minus sine squared x. Case 3 is when both m and n powers are even. Then we use half angle formula, which is sine squared x equal to 1 over 2 multiplied by 1 minus cosine 2x, and for cosine we have cosine squared x equal to 1 over 2 multiplied by 1 plus cosine 2x. There's a special case when both sine and cosine has odd power. When you face this situation, pick one that will give power of 2. To test your understanding, we should do a few examples. So, example, evaluate the following integrals. A. Integral of sine to the power of 3x cosine to the power of 2x dx. Now, to solve this, we have to transform sine to the power of 3x into sine to the power of 2x multiplied by sine x and keep cosine the same. And we then change sine squared x into 1 minus cosine squared x, and then we keep the last 2 trigonometric function the same. By then we can use this technique, which is let u equal to cosine x, so that our derivative will be equal to minus sine x dx, and then we will be able to get dx by exchanging the variables. From then on, plug u into places where there is cosine, and since dx equal to 1 over minus sine x du, we can eliminate sine x from the integral. From this step on, it's just basic integration. I'm sure you can do it. When we reach this step, we plug cosine x back into places where there are u, and then we will receive the answer right here. Integral of cosine to the power of 5x dx. Now, if you recall from the last slide, case 2, we have a situation where the power of cosine is odd, which is the situation we are facing right now. Now, to solve this, we have to transform cosine 5x to cosine 4x multiplied by cosine x dx. By then, we change cosine 4x into 1 minus sine squared x, which is the Pythagorean identity of trigonometric function, and we keep cosine x the same. From then we let u equal to sine x, so that our derivative will be equal to cosine x dx, and we will be able to exchange the variable to get dx, which will get 1 over cosine x multiplied by du. And from this step we can eliminate cosine x from the integral, and we'll be left with integral of 1 minus 2 u squared plus u to the power 4 dx. And again, from then on, just do basic integral. When you finish integrating it, plug sine x into places where there are u, and you will get the answer right here. Exercise C. When the power of sine and cosine are even, we use half angle formula to transform it, and using half angle formula we are able to get the new form of integral right here. From then we take 1 over 2 and 1 over 4 outside of the integral sign, and then we calculate all of the from then on we take 1 over 2 and 1 over 4 outside of the integral sign, and then just calculate these two factors. After you calculating it, you will be able to see that we cannot integrate cosine squared 2x and cosine to the power of 3 2x. Therefore, have to split the integral part by part. The first part of the integral right here is equal to x plus 1 over 2 sine 2x. However, with the second part of the integration, we have integral of cosine to the power of 2 2x dx. Now using half angle formula, we'll be able to calculate it, which we will get the answer right here. Now you should not plus the constant c to the answer yet, because we'll be adding it at the end when we combine all the answers together. Next, the last part of the integral is integral of cosine to the power of 3 2x dx. This is a case where power of cosine is odd. Therefore, we keep one factor of cosine and we change cosine squared 2x into 1 minus sine squared 2x. From then, using letting u equal to sine 2x, so that our derivative will be equal to 2 cosine 2x dx. This together, we will get the last answer right here. To solve trigonometric integrals inside the square root, we first have to use half angle formula to eliminate the square root. And here are the half angle formula. Now let's practice by doing an exercise. We have an integral from 0 to pi over 4 of square root of 1 plus cosine 4x dx. Using half angle formula, we'll be able to manipulate the old integral into the new form, and as our theta equal to 2x, therefore we will use half angle formula to change it to 2 cosine squared 2x. Therefore, we can transform our old function into the new one, which is integral of 0 to pi over 4 of square root 2 cosine squared 2x dx. And by then, we can eliminate the square root from cosine 2x and just do basic integration. You will get your answer, which is square root of 2 over 2. So the next part, which is products of sines and cosines. To solve an integral which have these forms, which are integral of sine mx sine nx dx, integral of sine mx cosine nx dx, and integral of cosine mx cosine nx dx, we must use identities provided below to transform our function to a new function which has the antiderivative that are easily found. Integral of sine 3x cosine 5x dx. Identities from the last slide will be able to exchange. We'll be able to transform this integral into a new one, which is 1 over 2 integral of sine minus 2x plus sine over 3 sine 8x dx. The new angle that we have is from letting 3 minus 5, and we'll get minus 2x, and 3x plus 5x will get 8x, which is, from then on you'll be able to just do basic integration and you will get your answers, which is here. The next and the last part of our subchapter, which is integral of power of tangent x and secant x. We integral of secant squared and tangent squared will be equal to tangent x and tangent x minus x plus constant c. However, when we have to integrate tangent and secant with powers higher than 2, we must use these identities here and here to integrate by parts when necessary to reduce the higher powers to lower powers. Let's do some exercise. A, integral of tangent 4x dx. First, we transform tangent 4x into 2 part, which is tangent squared x multiplied by tangent squared x itself. By then, we change tangent squared x to secant squared x minus 1 by using the identities right here. And then we multiply this factor by tangent squared x. You will get a new form of integral to integrate part by part. So first part of the integration, we let u equal to tangent x, so that du will be equal to secant squared x dx. When we do that, we get dx, and our dx will eliminate secant squared x from the equation, so we're left with integral of u squared. Just do basic integration and you will get your answer. Just combine the answers from your first and second integration. You'll be able to get your answers, which is 1/3 tangent squared x minus tangent x plus constant c. Now, to ensure that you understand the presentation thoroughly, I prepared a few exercises together. So evaluate the following integrals. First one, integral from 0 to pi over 2 sine squared 2 theta cosine cubed 2 theta d theta. In this, we must recall to the last slide. When cosine is odd, we keep one factor of cosine, and using the Pythagorean identity for trigonometric function to change cosine 2 theta into 1 minus sine squared 2 theta. And by then, let u equal to sine 2 theta, so that our du will be equal to 2 cosine 2 theta d theta. By then, we'll be able to find d theta and plug it into our old integral. U into places where they are sine 2 theta and plus d theta into the old equation. When we do that, we'll be able to eliminate cosine 2 theta from the integral, and we left with a more simplified version of integration, which will be able to integrate just using basic integration. And then, since sine of pi and sine of 0 equal to 0, we can say that we'll get the answer of our integral, which is 0. Next exercise, integral from minus pi to pi of sine 3x and sine 3x dx. Using the identities, we will be able to change our old form of integral into a new one, which is easier to find antiderivative of, which is integral of minus pi into pi 1/2 cosine 0 minus cosine 6x. Now we get the new angle because we use the old angle to calculate. When 3x minus 3x, we'll get 0, and when 3x plus 3x, we'll get 6x. And since cosine 0 equal to 1, we'll get a new form of integral right here. By then, just again do basic integration. You will get your answer right here. And since this is a definite integral, you must plug the value into places where there are x variable. By then, you're left with the answer, which is pi. I would like to add a little recap, which is for trigonometric integrals, it is important for you to remember and understand trigonometric identities, because without that, you may not be able to integrate trigonometric integrals efficiently. And even if you can use it by using different techniques, it will require a lot more effort and time, and it won't be as easy as just remembering the identities. That's all for my presentation on my term project. Thank you for paying attention, and goodbye.